Hello everyone, welcome to the 10th video of 10 AP Physics 1 summaries. Today we'll be looking at the mechanical waves and sound unit and focusing on conceptual review. If at the end of this video you are looking for more resources, please check out my description down below for links on more concept review and application problems. If you want to target your time towards specific content areas, I will include timestamps in the comments for each topic. Let's get started. A wave is a traveling disturbance that sends energy. Mechanical waves propagate through a medium. I say this to distinguish mechanical waves from electromagnetic waves that do not require a medium, like sunlight passing through space. In this video, we will discuss properties of longitudinal waves, transverse waves, and the many methods of analysis we have for waves in general. We have talked at length about simple harmonic motion in previous videos. As you know, when shown graphically, SHM appears as a sinusoidal waveform. Because of this, we already know the basics of wave analysis from the graphs of the mass spring oscillators and pendulums. So long as the x-axis is placed at equilibrium, the distance between the x-axis and wave peak represents a positive amplitude, and the distance below the x-axis and the wave trough represents a negative amplitude. We can identify periods in the same way, marking any distance that travels exactly 4 amplitudes total as one period. And lastly, frequency is still the inverse of period. Some new things when it comes to mechanical wave analysis are wave velocity and wavelength. When looking at a mass spring oscillator, there isn't a real concrete reason to assign either of those values. However, when it comes to mechanical waves, it is imperative that we understand these values. This unit is not very equation heavy, but here are the two major equations we will work with. On the bottom, we have our familiar friend, period is the inverse of frequency. On the top, we have lambda equals v over f, which means wavelength, or lambda, equals velocity over frequency. This equation is central to our understanding of mechanical waves, which we will explore in depth in just a moment. Before we do so, let's just make sure we understand how to manipulate the equation. At its core, this is just another adaptation of the equation velocity equals distance. In this unit, we are mostly working with periodic waves, which are regular propagations with constant period. Periodic waves are just a series of individual wave pulses strung together. When you picture a wave, you are probably picturing a transverse wave. Their defining feature is that the direction of propagation, i.e. the direction the wave travels in, is perpendicular to displacement. This is diagrammed by the vertical red arrows and the green horizontal arrow. If we are talking about wave pulses along a rope, we are talking about transverse waves. The other type of wave is a longitudinal wave. It's still a traveling disturbance, but the disturbance takes the form of pressure variations. If we are talking about a compressed spring or sound waves, we are talking longitudinal. In a longitudinal wave, the direction of propagation is parallel to the direction of displacement. As you can see on this GIF of particles, the red displacement arrow is parallel to the green velocity arrow. Variations in pressure are called compression and rarefaction. Compression is places where there is a high density of particles, and rarefaction is the opposite. Beware that longitudinal waves are graphically shown as transverse waves, and we can see this equivalency here. With pressure on the y-axis and time on the x-axis, compression is shown as a positive amplitude because of the peak in pressure. Rarefaction is shown as a negative amplitude because it is a trough in pressure. We show longitudinal waves graphically like transverse waves not to be confusing, but because drawing all of these little particles is impractical. Take a closer look at this particle or this red particle right here, colored so that it stands out amongst the others. Notice that it's not actually traveling the wave's velocity. In fact, none of the particles are. Rather, they're swinging back and forth between two positions with the pressure changes. That is because only the propagation is traveling on a constant velocity, and we can see this wave indicator showing that. The particles themselves are only reflecting a disturbance. When you hear sound, you are hearing changes in pressure of the air just surrounding your ear that has been knocked by the air around it. Whether transverse or longitudinal, the medium through which the wave travels determines its velocity. That means that high-pitched sound waves and low-pitched sound waves, even of any varying volume, travel at the same speed through the same medium. In the same vein, a single low-frequency pulse and a high-frequency periodic wave will travel at the same speed so long as they're on the same rope. You may have heard people compare the speed of light and the speed of sound. They can do this because the speed of sound through air is relatively constant, though it can vary slightly with temperature and humidity. In air, sound travels at around 767 miles per hour. It travels faster through water and even faster through solid materials because the particles are closer together, so disturbances propagate faster. The physical properties of the medium determine the velocity. An example of this is the equation V equals the square root of the tension force over the linear mass of a string. This equation will not be assessed, but I am including it to show that it is the tension and linear mass of the string itself that determine speed, not the frequency or amplitude of the wave. We can use the fact that the velocity of waves through a medium is constant to understand the relationship between frequency and wavelength. Their product equals the constant V. So when one of them increases, the other decreases, so V remains the same. If the wave passes through a change in medium, its motion will also be affected. Traveling from a denser medium to a less dense medium, a part of the wave will reverse and a part of the wave will pass through at a larger amplitude. Starting at a less dense medium and going into a more dense material, part of the wave will reflect back but flipped upside down, and part of it will pass through at a smaller amplitude. This will not be assessed, but I do think it's a good thing to be aware of. Here we can see transverse waves reflecting because the end of their medium is fixed partially or completely. If the endpoint is allowed to move vertically, a pulse will reflect back with the same amplitude as its original propagation. If the endpoint is completely fixed, the pulse will reflect back with the opposite amplitude. Remember that transverse concepts are all applicable to longitudinal waves, just replace positive amplitude with compression and negative amplitude with rarefaction. Reflection, along with the concept of superpositioning, serves as the foundation of our understanding of standing waves. Superpositioning is when two waves overlap. It creates interference, which can be either constructive, meaning the amplitudes sum to something larger, or destructive, meaning the amplitudes cancel out to some degree. On the left, we have two pulses of positive amplitude, summing to one larger amplitude, then breaking away as they continue their individual propagation. On the right, we have a positive and negative amplitude that almost completely cancel to zero amplitude before they pass through each other. Notice that waves do not permanently change amplitude after crossing. That brings us to standing waves. A standing wave is a wave that is constantly crossing its own reflection. The wave and its reflection superposition into patterns of destructive and constructive interference. Standing waves are sensitive to the length of their medium, otherwise the reflection does not overlap consistently after a few cycles. Here is an example of standing wave in action. The teacher is having his student hold the other end of the spring still. He's then manipulating the frequency of the wave by moving his hand faster or slower until he finds the standing wave frequency. As you can see, this happens at multiple frequencies. It creates a pattern of nodes, places of no movement, and antinodes, places of maximum movement. The student's end must be a node because he's holding it still. The teacher's end must be an antinode because he's moving it back and forth. There are certain conditions that must be met for a standing wave to occur, such as the required locations of nodes and antinodes, the length of the string, and the wave velocity of the string. In application problems, we see these restrictions vary based on the physical situation. On a string, we usually consider both ends to be nodes. Think of a guitar. Both ends of the strings are kept still, so the standing wave produced must have nodes at both ends. In an open tube, we consider both ends antinodes. Air is free to compress and rarefact freely in and out of each end of the tube. In a half-closed tube, we consider the closed end a node and the open end an antinode. Air is not moving around the closed end, but it is free to compress and expand out the open end. Each of these sets of requirements supports a different fundamental frequency and wave shape. The fundamental frequency is the lowest frequency that can be sustained as a standing wave on a given length. It is also called the first harmonic. On the top, we can see the fundamental frequency on a string that has two nodes, one on either end. The fundamental is only half of a wavelength here. This means that the fundamental has a lambda of 2 times the length of the string, and you can imagine it going, here's half of a wavelength, down, here's a full wavelength. Below we have a half-open tube scenario. With one node and one antinode, the lowest possible frequency this can support is 1/4 of a wavelength, and if we follow similar reasoning, we can imagine tracing it out. That makes this fundamental frequency have a lambda of 4 times the tube length. The fundamental frequency is the first harmonic. Below the first harmonic, we have the second harmonic, which is also called the first overtone. The second harmonic is the next lowest frequency that can be sustained as a standing wave, and so on with each harmonic after it. For some general rules to solve these types of questions, it helps to draw the waveform so that you understand the location of nodes and antinodes. When confronted by questions on this, it is helpful to use the length of the tube or string and the number of wavelengths to solve for lambda. Also, be sure to identify what you know in the equation lambda equals velocity over frequency and use to solve. In situations where the wave is bookended by nodes, this is pretty straightforward. The harmonic number correlates directly to the number of half wavelengths, or these bumps that you can see. This is also true for antinode-antinode situations because they're basically the same, just shifted over a quarter of a cycle. Node-antinode situations, on the other hand, are a little bit more complicated. In tubes, this is how harmonics are related to wavelength. I'm tracing out a single wavelength in each tube in green to show you what fraction of a lambda the harmonic is made of. Remember that this comes from finding the lowest frequency that is bookended by antinodes in the case of open-open, and the lowest frequency that is bookended by one node and one antinode in the case of half-open. The former ends up occurring at every multiple of 1/2 lambda, and the latter occurs at every odd multiple of 1/4 lambda. Beats are another case of wave superpositioning, except this time the waves have different frequencies. When two tones of different frequencies are played simultaneously, you hear a wavering tone that wobbles according to the difference of the original tone's frequencies. It's only noticeable, though, when the frequencies are relatively close together. Here is an example using tuning forks. It's because one of the frequencies becomes slightly more and more out of phase with the other that they switch between constructive and destructive interference and make this wavering noise. The beat frequency is very simple. It's just the difference between the original frequencies. When we talk about sound waves, there are two values that can be easily confused: pitch and volume. Pitch is based on the frequency, which is measured in hertz. Higher frequency, higher pitch. Your ear interprets the quantity of pressure variations as either high-pitched or low-pitched depending on how many there are. Volume, on the other hand, is based on the amplitude of the wave, and it's measured in decibels, a logarithmic unit. If you've ever been to a large concert and the music is so loud that you can feel it in your body, you are feeling the big fluctuations in pressure that come from high-amplitude sound waves. For example, if we have a car revving its engine, I would subjectively call it low-pitched and loud in volume. This makes it a low-frequency, high-amplitude sound. If we instead have a bird singing, I would call it high-pitched and quiet. This translates to high-frequency, low-amplitude. And lastly, the Doppler effect. If you've ever heard a siren rush past you, you're probably familiar with this phenomenon. What is happening here is that the frequency you're observing is different than the frequency the car is emitting. From the perspective of the driver, the frequency is constant, because the source of the sound is constant relative to them. To an outside observer, the sound source is moving. This causes the sound waves to compress and appear as a higher frequency when the car is approaching you because it is driving into the sound waves it makes. Then, as the car drives away, the sound waves seem to be spread out and lower in frequency. This also implies that there is no gradually increasing frequency as the car gets closer. It's either higher or lower, but it doesn't slide. Also, the velocity of sound is still not changing, just the perceived frequency. And with that, we have finished reviewing the AP Physics 1 curriculum. Thank you so much for watching, and be sure to check out the description down below for more resources and more about me. Good luck to current AP Physics students.